Hi there, this is Surajit and you are welcome to our channel. In last video lecture, we have talked about gradient curl divergence. So we have learned how to write gradient curl divergence in different coordinate system and what are their physical meaning. So in this video lecture, we'll talk about two important theorem, Stokes theorem and divergence theorem, and one important function, Dirac delta function, and we'll see why these theorems are so important for the study of electrodynamics. Okay, so let's dive in. So we'll start with the Stokes theorem. So right here, Stokes theorem. Stokes theorem. So what is said in Stokes theorem? For that, let me just draw a closed loop here. Let's say this is some arbitrary closed loop C, and the area, the surface that is bounded by this closed loop, that's area, let's say S. S, and consider a vector quantity A in this region. Then according to this statement, according to the statement of the Stokes theorem, what we can write here, so the line integral of a vector along the closed loop C is equals to the surface integral of the curl of the vector A over the surface that is enclosed by the closed loop C. Closed loop C. The line integral of a vector along a closed loop C is equals to the surface integral of the curl of this vector A over the surface that is bounded by the closed loop C. So that is this surface. This is the surface. Over this surface, if we first take the curl of this vector, and then if we take the surface integral over the surface, so both will give you the same result. Both will give you the same result. So this is the Stokes theorem, statement of Stokes theorem. And now let me give you one example and we'll see what is the beauty of this Stokes theorem. What is the beauty of Stokes theorem? So for that, let me draw here a closed loop. Let's say this is a closed loop, and also consider some current distribution inside the closed loop. Okay, so these are somewhere through which current is flowing, and let's say in this where current is I1, in this where current is I2, in this where current is I3. Current is I3, and let's say sum of this all three current I1 plus I2 plus I3 is equals to 0. I3 equals to 0. So now what I am going to ask you, let's say calculate the magnetic field due to this three pair, and let's say magnetic field is B, and if you take the line integral of this magnetic field along this closed loop, what will be the value of this line integral? P dot dl. So I think we all know, according to, we have learned in 12th class that the line integral of magnetic field along a closed loop is equals to the mu naught current enclosed by this loop. Current enclosed by this loop. So in this case, enclosed current is 0. So B dot dl will be 0. So now looking at the result, simply looking at this result B dot dl, along this closed loop C, if we get 0, what we can guess about the magnetic field? Or what about this result? How we can explain this result? We can say that this magnetic field over this loop is everywhere 0. That's why we are getting 0. That could be the one guess. Another guess, everywhere this magnetic field is perpendicular to this length of this loop. That's why it is 0. But the main thing that we'll not get from this line integral, that is why I mean this magnetic field is generated because of some current distribution. So if we want to see the how this current is distributed, and because of that how this magnetic field actually is generated, so if we want to see how this current is distributed inside this loop, then what we have to do? From this line integral we will not get any idea how this current is distributed. Only we will see from outside that the total current is 0. Total current is 0. That's why this is 0. Or other way we can say the magnetic field at everywhere perpendicular to this length, that's why 0. Or we can say that the everywhere magnetic field is 0 from this loop, and that's why 0. But we cannot get any idea how this current is distributed inside the loop. How this current is distributed inside the loop. Or we can say we cannot get the idea how this magnetic field is behaving everywhere, each point inside the loop. Only this line integral what we can get idea how this magnetic field is rotating along this loop. But if we want to see what is going on inside, how this magnetic field is behaving at every point, or we can say how actually current is distributed over this loop. If we want to see this current distribution, then what we have to do? We have to do second part. We have to take the curl of this magnetic field. When you take the curl of the magnetic field, that will give you current distribution. And you will see at some point current distribution will be positive and some point current distribution will be negative, and because of that actually a magnetic field at different point will be a different direction, and that's why you are getting the final answer 0. So looking at this line integral only, we can say that how this magnetic field is rotating around this loop. But if we want to see what is going on inside, then actually we have to do this part. First we have to take the curl of this vector. So when you take curl of this vector, that will give you the information of each point inside this loop, and from the surface integral again you will get the same result from both sides. Okay. And there are another theorem that is called divergence theorem. Divergence theorem. So what has been said in this divergence theorem? For that again let me draw a arbitrary closed surface. So this is a closed surface, let's say S, and that volume that is enclosed by this closed surface, let's say that volume is V. Volume is V, and consider a vector in this region A. Then according to this theorem, what we can write here, the surface integral of this vector A over the closed surface S is equals to the volume integral of the divergence of this vector A over the volume V that is enclosed by this surface. Okay. So what is said in this divergence theorem? says that the surface integral of a vector over a closed surface is equals to the volume integral of the divergence of this vector over the volume that is enclosed by this surface. Enclosed by this surface. So again, let me give another example, and from there we can understand the beauty of this theory. Let's say we have a spherical surface, and inside this spherical surface we have a dipole, plus q and minus q. Dipole. Now if we calculate the electric field because of this dipole over the surface of this sphere, and if we calculate the surface integral over this sphere of this electric field, so what we'll get? We'll get, according to Gauss law, again we learned in 12th class, that surface integral of electric field along any closed loop is equals to qy, q enclosed divided by epsilon naught times. So in this case, total charge will be 0. So again we'll get E dot ds equals to 0. So again, from the surface integral, what we can say? We can say that the surface integral 0 because total enclosed charge is 0. That is one guess. Another guess, we can say this electric field everywhere on the surface is 0. Or we can say everywhere electric field is perpendicular to the surface. That's why maybe this surface integral is 0. So looking at the surface integral, again, we'll not get any clue how the charge is distributed inside the volume. How the charge is distributed inside the volume. If we want to see how this charge is distributed inside the volume, then what we have to do? We have to use this theorem. We can use this theorem, and then using this theorem we can write this way: surface integral equals to the volume integral of the electric field, divergence of this electric field. So when we will take divergence of this electric field, that will give you the source of this electric field, that is charge, how this charge is distributed inside the volume. How charge is distributed inside the volume. So if you want to see how this, I mean, if we know the electric field over a bound surface, and if we do the surface integral, we can find out the electric flux, but we'll not get any idea how this charge is distributed inside the volume. But if we want to see how this charge is distributed inside the volume, for that what we have to do? We have to do this part. We have to take the divergence of the electric field inside the volume, and then if we do the volume integral over the surface, then we'll get the same result both the case. But this part will give you picture of what is going on inside, and this side will give you how this flux is passing through this closed surface. Okay. And also this is the one way to look at this theorem, and other way we'll get some problem like this way. Let's say we have a cubic surface. You have a cubic surface. So we know cube have 6 surface. So now if we know the electric field inside this cubic surface, and if we want to calculate the flux, then what we have to do? We have to do the 6 integral for 6 surface. But if I use this theorem instead of surface integral, if we convert it into replaced by this volume integral, then what we have to do? Only we have to first calculate the divergence of this electric field, and then from the single volume integral we can calculate what will be the flux. So it will be easy to calculate the flux. This type of, so it will take a little bit less time compared to the surface integral, So for that purpose also, I mean, we are also preparing for competitive exams, so definitely we'll try to adopt that process which will take the less time to solve a problem. So whenever we'll get this type of problem, let's say we have a closed surface, like cubic surface, and then we, or cylindrical surface also. If we want to calculate the flux over the cylindrical surface, then we have to calculate flux through this surface, through this surface, through this surface of this electric field. But if we do the volume integral, then what you have to do, you have to just write the divergence of this electric field inside the volume, and then over the volume, if we take the volume integral, that will give us a flux. That will also give us the flux. So we can, I mean, we can use this theorem there also. Yep. So now we understood what is the beauty of Stokes theorem and divergence theorem. So now we'll define another function, and when this function is also very important for the study of electrodynamics, and that is Dirac delta function. So right here, Dirac delta function. So the idea is like this. Let's say we have a function which height is h and width is x, and let's say this is a x equals to a point. So we are around the x equals to a point, we're considering a function whose width is delta x and height is h. Height is h, and one more condition, the area under this curve, let's say unit. Area under this curve unit, then what we can write, delta x into h, that is equals to 1. Delta x into h, that is equals to 1. Now if we shrink the value of x, that's mean if we reduce the value of delta x, what will going to happen? Area will remain same, area will be always unit, then height of this function will increase. Now if this is the width of this my function, so keep the area constant, what we have to do, we have to increase the height. We have to increase the height. So more we reduce the value of x, value of delta x, the height of this function will increase more. Increase more. So now if we consider a situation where delta x tends to 0, where width tends to 0, width is very small, then what will be the value of h? H will become almost infinite. It's very high value. That time we can represent like this. At x equals to a, this function have infinite value, and other point, this function will be 0. So this type of function is called Dirac delta function. And how we represent this Dirac delta function? We represent in this way, delta x minus a. So that will give the location where this peak is located. So this will be the infinite when x equals to a. At x equals to a, it will be infinite, as we have noticed here. Then what will be the value of this function at other point? Other point, it will be 0. Otherwise it will be 0. So this is the definitions of Dirac delta function. At particular point, the value of this function will be infinite, and other point it will be 0. The other point it will be 0. Now what we have to learn here, we have to learn some properties of this Dirac delta function. Properties of Dirac delta function. This function has so many properties, but we'll discuss only those properties which will be required for the study of electrodynamics. So first properties is of the area under the curve is unit. As we have seen, the area under the curve is unit, and we can write this in terms of mathematics in this way: delta x minus a into dx, and if we integrate from minus infinity to plus infinity, that will give you 1. That will give you 1. And sometimes instead of this infinite limit, we get finite limit. Let's say b to c delta x minus a into dx. So now this value, this integration of this value will be depends on the limit of this integration. So let me draw a figure here. Let's say this is our x-axis, and this point is x equals to 0, and this is a point when x equals to a, where this Dirac delta peak is located. Now if we consider this limit, let's say this is my x equals to b point, and this is my x equals to c point, then you can see here this x equals to a point is lies between b and c over this limit, inside this limit. Then this integration of this limit will be, the value of this integration will be 1. Value of this integration will be 1. So when this integration will be 1, when a is lies between b and c. Otherwise this will be 0. Otherwise this will be 0. Okay, this is the first property of Dirac delta function. Now second properties, for that let's say this is my x-axis, and along y-axis I'm drawing a function. This is a function of x, and let's say some continuous broad-bed function. This is a function, continuous function. And then we have also consider, let's consider our Dirac delta function at x equals to a. Equals to a, we have a Dirac delta function. This is some arbitrary function f of x, and this is a Dirac delta function. So now if we product these two functions, what we will get? F of x is a continuous function, and then we are multiplying with this function with the Dirac delta function, whose peak position at x equals to a. What we'll get? We'll get, see, this Dirac delta function has properties. It will have infinite only at x equals to a, and other point the value of this Dirac delta function is 0, and product, in this product, if one function is 0, then the product will be 0. Product will be 0. So only at x equals to a will get non-zero value, and apart from that the other point will get 0 value, because at other point this Dirac delta function will be 0. So what will be the value of this product at x equals to a? At x equals to a, we will get some particular value of this function, so we can replace the value of x of this function by a, and into this Dirac delta function. So this will give us f of a into delta x minus a. Delta x minus a. And then what is the third properties? Third property is, if we integrate this whole function, I mean if we multiply a function with the Dirac delta function, and then if we integrate this function over the certain limit, let's say b to c, what we'll get? So you can use this property, second property is here. So according to second property, what we can write, if we multiply a function with the Dirac delta function, what we'll get? We will get the value of function at the peak position of Dirac delta into the value of Dirac delta function. So if we replace this thing here, what we'll get? We'll get f of a into delta x minus a to dx from b to c. From b to c. Now, as soon as we'll replace this function, in this function, if we replace x by a, that means this function will give you a particular value. So this will be constant. We can take it outside from the integration. So remaining term, what we'll get? We'll get b to c delta x minus a into dx. Now this will be 1 when x equals to a point lies between b and c, otherwise this will be 0. So finally what we'll get? We'll get f of a if a lies between b and c, otherwise we'll get 0. Otherwise this will give us 0. Okay. So this integration f of x delta x minus a will be equals to the f of a when the position of peak, Dirac delta peak, is lies between this limit, over this limit, inside this limit. If it is not, then this value of this integration will be 0. Okay, value of this integration will be 0. And then fourth property is, sometimes we'll see Dirac delta itself is a function of, usually it's a function of variable x, but sometimes we'll get a Dirac delta function itself, it's a function of a function. And instead of variable, Dirac delta is written like this, gx, where gx is some function of x. Gx is function of x. So to solve this type of Dirac delta function, what we have to do, if we want to see by looking at this function, we cannot guess where is the position of this peak, Dirac delta peak, until we write in this form, in the variable form. So what we have to do, we can write this Dirac delta function in terms of variable. So for that, what we have to do, we can use this relation, delta x minus xi divided by mod of g dash xi, where I goes from 1 to n. Now what is xi here? Xi are the roots of a function, or root of the equation, or root of the function equation. Gx equals to 0. if we make this gx equals to 0, so we'll get some value of x, and that x is represented by xi. So this is the solution of this gx equals to 0, this equation. Gx equals to 0. Okay, so let me give one example. From there maybe it will be clear. Let's say we have a Dirac delta function like this, x square minus s square, x square minus x square. So in general, you see here we have defined this Dirac delta function in terms of x only, but this is function of x square. So in this type of situations, what we have to do, we have to write first this way: delta is a function of gx. Dirac delta is a function of function. Now we have to identify gx. So if we compare these two, what we'll get? We'll get gx is equals to x square minus s square. Okay, x square minus x square. So once you know this function, then what we can write here, delta x square minus x square is equals to summation over delta x minus xi divided by mod of g prime x, and I will goes from 1 to n. So what is g prime here? G prime is the first derivative of c. G prime is the first derivative of dg by dx. Okay. So now what we have to do, if we want to write this Dirac delta function in terms of variable, so first we have to make this equals to 0, gx equals to 0. So when you write gx equals to 0, what we'll get? We'll get x square minus s square. This is equals to 0. So we'll get value of x, that is plus minus a. Value of plus minus a. Now how many terms will be there? What is the value of I from 1 to n? Where this n will depends on how many roots this function has. If you get 2 roots of this equation, then we'll get 2 terms here. If you get 3 roots of this equation, then we'll get 3 terms here. But in this case, we are getting we got here 2 terms, x equals to plus a, x equals to minus a. So in this case, it will have 2 terms only. So how we can write this? But before that, also we have to find out the first derivative of gx, that is dg by dx. So what we'll get here with 2x, it will be 2x. So now if we put the value of xi here, so in this case xi is plus a and minus a. So if we put first plus I, so what we'll get? Plus a, we'll get delta x minus a, and then first we have to take the first derivative, and that will be first derivative of gx, that will be 2x, and now we have to replace this value of x by first solution, that is x equals to a. So to replace it, what will get? 2a. Mod of 2a will be 2a plus second term associated with second roots. So second roots here, x equals to minus 1. So xi will be in this case minus 1. So what we'll get here? We'll get x minus, and already there is minus, so it will be plus, divided by, if we put x equals to minus 1 here, what we'll get? Minus 2a, but we have to take mod, so this will also give you plus. So finally what we'll get here? We'll get 2a delta x equals to delta x minus a plus delta x plus a. Delta x plus a. Okay. So in this case, gx is a function of x square. So we got two solutions because of that. In this expression, we got only two terms. If we get a function like this gx function of x cube, then we'll get three solutions, and for that time we'll get three terms here. Okay. So this way we can represent when we get a Dirac delta function itself is a function, the function of another function. Then first we have to write the Dirac delta function in terms of variable. When you write this variable, then only you will get the idea that where is the peak is located actually. So in this case, see, first peak will be at x equals to a. So if you want to calculate the or want to see the location of the Dirac delta peak, what you have to do? You have to do this x minus a. What is the bracket term? That if you make that 0, from there what will be the value of x? That will give you the position of Dirac delta peak. So in this case, x minus a equals to 0. If you put x minus a equals to 0, you will get x equals to a. And for this term, if you put x equals to x plus a equals to 0, we will get x equals to minus a. So you will get actually two Dirac delta function at x equals to a and x equals to minus a. Okay. So I think these are few properties. If you remember these properties, then it will be very, very easy to solve this problem. Okay. And now one important concept we learned here. Using this Dirac delta function, we can represent actually a point function, point charge as a continuous charge distribution. So right here, with the help of Dirac delta function, with the help of Dirac delta function, we can represent point charge as a continuous charge distribution. Continuous charge distribution. Okay. Continuous charge distribution. So let's make one example. Let's say this is xy plane. And we have a point charge q at x equals to a. X equals to a. Now this point charge we can represent as a surface charge, as a linear charge, or as a volume charge. So if we want to represent this point charge as a linear charge, so write here linear charge distribution. That's mean since this charge is distributed on the x-axis, so we can write charge per unit length on the x-axis, lambda function of x, can be represented in this way: q, the amount of charge, and then what we have to multiply with here, Dirac delta function at the position of charge, q del x. this will give you linear charge distribution. So how it will give you linear charge distribution? For that, okay, let me just come back here. Properties of Dirac delta function. You see in this equation, when we'll multiply dx with this Dirac delta function, we'll get a dimensionless quantity. We'll get a dimensionless quantity. So now this dx, what it will represent? It will represent a length. It has dimension of length. So what will be the dimensions of one dimension Dirac delta function? It will be inverse of length. So one dimension Dirac delta function, dimensions of one dimension Dirac delta function will be 1 by length. 1 by length. So in this case, this Dirac delta function has dimension 1 by length, and this is charge. So how we'll read this? Charge per length, coulomb per meter. So that will give you charge per unit length. Charge per length, that is linear charge distribution. Linear charge distribution. So when we representing this point charge in this way, q into our Dirac delta function, that will give us actually a linear charge distribution. So in this way, we can represent a point charge as a linear charge distribution. But for that, what we have to do? We have to prove that the total charge will remain conserved. So if we want to calculate total charge, what we have to do? Total charge lambda x. We know the charge per unit length on the x-axis. So now we have to integrate from minus infinity to infinity. If we integrate, what we'll get? We'll get total charge, and that charge must be equal to the q. If it is q, then we can argument that. So this definitions is representing charge per unit length, and also it is representing the total charge, which is equal to the q. That's mean we can represent this point charge as a linear charge. So let's do this integration. So put the value of lambda x here. So what we'll get? We'll get q delta x minus a into dx, and then we have to integrate from minus infinity to plus infinity. Q is constant, you can take outside, and you have to integrate minus infinity to plus infinity, delta x minus a into dx. That will give you 1. This integration will give you 1. So finally what will get? Q. So we are getting total charge q, that's equal to exactly the amount of charge we have placed here, same charge. Okay, so that's mean, so this mathematics, the way we have represent here, we can say that this represent a charge per unit length. It says dimension, charge per unit length, and it also gives the same charge that we have placed here. So in this way, we can represent a point charge as a linear charge distribution. And also we can represent a point charge as a surface charge distribution. So right here, surface charge distribution. Surface charge distribution. So how we can represent surface charge distribution? For that, let me draw another figure. Let's say this is x-axis, this is y-axis, and this is a point where we have placed a point charge, let's say q, and the coordinate of this point charge, let's say x0 and y0. X0, y0. So we have placed a point charge in the xy plane. The amount of charge is q, and it has coordinate x0, y0. So now we can represent using the Dirac delta function. In this case, we have to use two-dimensional Dirac delta function. So using the two-dimensional Dirac delta function, we can represent this charge as a surface charge. So in this case, we have placed charge in xy plane, so it will be a function of x and y is equals to, how we can write this point charge as a surface charge. For that, First we'll write the amount of charge, and then we'll write the Dirac delta function at x equals to x naught, and x equals to y equals to y naught. Y equals to y naught. Either you can represent in this way, or if we just join this to this point with the origin, we'll get a vector. And if this vector, let's say r naught vector, then what we can write, sigma xy is equals to q. For 2 dimension, we'll write 2 here, then r minus naught. So in this case, we'll get a Dirac delta peak at r equals to r naught, because charge is only at this position and other point charge is actually 0. Other point there is no charge distribution, only this charge is concentrated at this position, and since this volume is very very small, so charge per unit volume will be very very high. Very very, in this case, charge per unit area will be very very high. So at this point it will goes infinite, and other point this sigma will be 0. Sigma will be 0. So here also you can see that the dimension of this charge distribution, if one dimension Dirac delta function has dimensions length, and 2 dimension it will be 1 by area. So in this case, this will the dimension of this part will be 1 by area, and this is charge, so charge per unit area, that will give you surface charge distribution. Surface charge distribution. And if we integrate over the xy plane, whole xy plane, we'll get the total charge. And in this case, you can see when you take the integration of this term over the xy plane, that this term will give you 0, this term will give you 1, so total charge will be q. So this way we can represent the point charge as a surface charge distribution. Surface charge distribution. And also we can represent surface charge as a volume charge. Volume charge distribution. For that, let me just draw another figure. Let's say this is x-axis, y-axis, and z-axis, and we have a point charge in the space whose coordinate is, let's say, x naught, y naught, and z naught. So at this position we have a point charge q. Now we want to represent this point charge as a volume charge all over the space. Over the space. So how we can represent this point charge as a volume charge? So in this case, we can write rho, which is function of x, y, z, is equals to, first we'll write the amount of charge, and then we'll write position of this Dirac delta function at the position of this charge, that is x equals to, when x will be x naught, and y will be y naught, and z will be z naught, then only there will be an infinite amount of volume charge, and at other point 0. So it's the same idea. We have placed a point charge here, but we want to calculate the volume charge, that is charge per unit volume. So any other point, if we consider a volume, the charge per unit volume will be 0. But if we consider a volume here, that since charge is concentrated in this position, whole charge, q charge is concentrated in this position, so charge distribution in this position will be very very high. So we can represent in this way. And sometimes also, again, you can, if we added this 2 point, the position of charge with the origin, let's say if this is represented by a r naught vector, then we can also represent in this way rho, which will be function of x, y, z, or x, y, z is equals to q. In this case, we'll write del q r minus r naught vector. So when r equals to r naught, that is at this position, charge density will be very high, and at other position charge density will be 0. Other position charge density will be 0. So what will be the benefit by representing a point charge as a continuous charge? That we'll see in later when we talk about Gauss divergence theorem. We'll see there some example. Okay. And one more important concept that we need to discuss here. So this is special note, you can write here notes. Let's do exercise. We know how to calculate divergence. We know how to calculate surface integral. We know today we have learned divergence theorem, Stokes theorem. So let's consider a sphere of radius r and its origin. The center of the sphere is at the origin of coordinate system. X-axis, this is y-axis, this is z-axis, and this is a spherical surface of radius r. Spherical surface of radius r. Now if we place a point charge at the center of this sphere, q charge. So after placing this point charge at the center, if I ask you what will be the electric field at this position at a distance r from the center of the sphere, I think that you can write. And this distance is r. Electric field in this case it will be radial outward direction because charge is placed at the center of the sphere. So we can simply write that electric field at position r will be E equals to q divided by 4 pi epsilon naught r cap divided by r square. This will be the electric field at a distance r from the center. So now if I ask you what will be the electric flux over this surface, or what will be the surface integral of this electric field over this spherical surface, Okay. So what we have to do for that, first we have to consider a point on the surface, and then we'll consider elementary area around this point. So what will be the area? In spherical polar coordinate, we have written in, I think when we talk about the spherical polar coordinate, that day we have learned how to write the spherical elementary length on a curved surface of a sphere. We can write this ds in this way. Ds vector is equals to r square sine theta d theta d phi. Since the radius of the sphere is capital R, so on the surface everywhere r will be fixed. So that's why I replace the small r by capital R. So capital R square sine theta d phi. And what will be direction? Directions will be r cap in this direction. Okay. So now if we want to find out the surface integral, so what we have to do? First we have to calculate the electric field at this position. So for this position, what will be the electric field? Simply we have to replace the small r by capital R. When you extend this point from here to here, so at this point the small r will be capital R. So what will be the electric field? Electric field on the surface will be q divided by 4 pi epsilon naught r cap divided by capital R square, and then we have to multiply with this elementary area. This will be r square sine theta d theta d phi r cap. So r cap dot r cap, that will give you 1. And for complete spherical surface, what will be the limit of theta? Limit will be 0 to pi. And what will be limit of phi? 0 to 2 pi. So what this will give you? This will give you simply 0 to pi, 0 to 2 pi, and then q divided by 4 pi epsilon naught r square into r square sine theta d theta d phi. Now this r square will cancel out. So what will it get? Q divided by 4 pi epsilon naught, and then we'll integrate sine theta 0 to pi. We'll get sine theta into d theta, and we'll integrate d phi 0 to 2 pi. When we integrate, from this integration we'll get 2, and from this integration we'll get 2 pi. So finally we'll get 4 pi. So this integration will give us 4 pi, and this 4 pi will cancel out. So what we'll get q divided by 4 pi epsilon naught. From sine theta term we'll get 2, and from cos theta this d phi term will get 2 pi. So this will give you 4 pi. So when you cancel out 4 pi, you will get q by epsilon naught. Q by epsilon naught. Okay. Now what we have to do, let's do this volume integral of this electric field. Or let's just use the divergence theorem. So according to divergence theorem, what we can write? Divergence theorem said that the surface integral of a vector along a closed surface is equals to the volume integral of the divergence of this vector. So in this case, E vector. First we have to take divergence of this E vector, and then we have to integrate over this volume. We have to integrate over this volume. So for that, from surface integral we get this result. Now what we have to do, we have to calculate volume integral of this electric field over this volume, and let's see if we get same result or not. Can we get the same result or not? What we have get from surface integral. So for that, what we have to do, first we have to write the divergence of electric field. So put the value of divergence here, electric field here, q divided by 4 pi epsilon naught r cap divided by r square. This is the electric field inside the volume at any point, the distance r, because we have to take the divergence of this electric field inside the volume, not on the surface, inside the volume at any arbitrary point. So at a distance r, the electric field will be this. So now we have to take the divergence of this electric field. So now if we this q by 4 pi epsilon naught constant term, so we can write it here, q divided by 4 pi epsilon naught. So what we have to do, we have to take the divergence of this vector quantity r cap divided by r square. R cap divided by r square. So here r cap, that means it's a spherical polar coordinate. So the vector is given in spherical polar coordinate. So what you have to do, we have to use the definitions of divergence in spherical polar coordinate system. What will be the definition? We have learned in last class, divergence of any vector, if it is in spherical polar coordinate, then what you have to write? We have to write h1, h2, h3. So in this case, it will be r square sine theta. And then r component. Here vector have only r components, will write only r component. So for that, first we'll write del by del u1. So u1 in this case will be r. So del by del r, and then we have to multiply h1, h2 and h3. So in spherical polar coordinate, h1 is 1. H1 is 1, but h2 is r, and h3 is r sine theta. So you have to multiply here h1, h2 and h3. So that will give you r square sine theta, and then first component of vector, that is r component of this vector, r square. R square. So now we have to differentiate with respect to r, so we can bring this sine theta outside. So when you take it out, what we'll get 1 by r square, and then del by del r, and this r we can cancel out, we'll get 1, and then differentiation will be 0. So if this divergence is 0, then what will get? What will be the value of this volume integral? This volume integral will give us 0. This volume integral will give us 0. But according to divergence theorem, since we get the value of surface integral q by epsilon naught, so if we calculate the volume integral, we are supposed to get the same result, q by epsilon naught. But why we are getting a 0? So either this statement is wrong, Gauss divergence theorem is not correct, or we made something mistake here. Divergence of this electric field. So you see here, when you take divergence of this electric field, that will actually give you the idea how this charge is distributed over the sphere. So you can see that there is only point charge at the origin. So at other point there is no charge. So all other point, this divergence of this electric field will be 0. But at x equals to r, at r equals to 0, we cannot cancel out this r and r. We cancel out this r only when this r not equals to 0. So at r equals to 0, this will not be 0. At r equals to 0, this will not be 0. So this definition is not valid for r equals to 0. So this will be 0 when r not equals to 0. R not equals to 0. But you see, we have to calculate this volume integral over the whole volume. Over the volume. So this r equals to 0 point also inside the volume. Inside the volume. So in this type of situations, we have to do this divergence of this type of vector in a different way. Different way. So what we can do here, look at the surface integral, what we get q by epsilon naught. So we can get some result of this divergence of this electric field in such a way so that from the volume integral also we get the same result. Volume integral can get same result, and we'll get same result only when we can write this divergence of this vector. Divergence of r cap divided by r square is equals to 4 pi del cube r. So this suggests that when r not equals to 0, this divergence will be 0, but at r equals to 0, it will be infinite. That is supposed to be. We have a point charge, so charge is concentrated at the origin only. At this origin, charge density is very, very high, but at other point there is no charge. That point is no charge. So whenever we get this type of vector, whenever we're going to solve, when we solve the problem in any step, we get this type of vector r cap divided by r square, and if we want to write the divergence of this vector, we'll write this 4 pi del cube r. 4 pi del cube r. So now if you write the divergence of this vector in this way, 4 pi del cube r, so then what we'll get? We'll get divergence of E dv. So if we take the volume integral of this term, what we'll get? So if we replace this divergence, value of this divergence here, what we'll get? Q divided by 4 pi epsilon naught, and then value of this divergence we have written here 4 pi del cube r, and then we have to volume integral over the volume of the sphere. So this 4 pi will cancel out, q by epsilon naught you can take outside, and del cube, that is 3-dimensional Dirac delta function, and we have to volume integral. I have to take this volume integral over the volume. So now for 3-dimension case, just like 1-dimension case, when we integrate this limit of v to c delta x minus a dx, that will give you 1 when this x equals to a point lies between b into c. Same way for 3-dimension, if the position of Dirac delta function lies inside the volume over which we are actually taking this volume integral, if r equals to Dirac delta, peak of this Dirac delta lies within this volume, then this integration of this volume will be 1, and otherwise it will be 0. So in this case, we have to take the volume integral over this volume, and the Dirac delta function is a peak of the Dirac delta function at r equals to 0, that is at the center of the sphere. So this point is lies within the volume, so this volume integral will be 1. So if this volume integral 1, then what we'll get? We'll get q by epsilon naught. So now see, from the volume integral and from the surface integral, we are getting the same result. We are getting the same result. So in different way, you can say whatever we have guessed here, that is correct. This is correct. So from today, if we get something, any vector like this, r cap divided by r square, and if we want to calculate the divergence of this vector, we will always write in this way, 4 pi del cube r. 4 pi del cube r. And then if I ask you, instead of this, if we have a vector like this, let's say a vector is equals to r cap vector divided by r minus r naught whole square, where r cap is the unit vector, r cap is the unit vector along r minus r naught. Along r minus r naught. If we get a vector like this, and if we want to take the divergence of this vector a, what we should write from this result? Here we have divergence of r cap divided by r square, and this r cap is the unit vector along r. This r cap was the unit vector along r. So from same result, if I ask you what will be the divergence of this vector, where this r cap is also unit vector along this r minus r naught vector. So this will give you actually same result if I tell you only the peak of the Dirac delta function will be at r equals to r naught. R equals to r naught. Okay. So if we get a vector like this, then we'll write this way, 4 pi del cube r minus r naught. And if we get a vector like this, then we'll get divergence. This is equals to 4 pi del cube, or in this case, peak of the Dirac delta function will be at r equals to 0. Okay, r equals to 0. Okay, so this mathematics, I mean, whatever we have discussed so far, that will be enough to understand the electrodynamics. So today I will upload a practice set, and questions will be related to the concept that we have discussed so far. And also this week, I mean, I will travel somewhere for coming to 3 days. So for that reason, I am not able to upload a video lecture for 2-3 days. But meantime, you can practice, you can solve this practice set that will upload today. You can check the community section of our YouTube channel. There I will upload the practice set, so you can practice the problem, and then when I will come back in next week, we'll start the electrostatic part. Okay. So thank you for watching. See you in the next week.